So hi, I'm Ellie and I'm going to talk about my work on new precursors to printed electronic metal oxides. I have to...
Just use the key and use
Okay, so to start off with, I'm going to talk you through the background of the project, the printing process and the materials that we're looking at. I'm then going to talk about precursor design and the synthesis that we used, and then the results. So electronics are all around us and play a really important role in everyday life. And because of this, there's an interest in developing new electronics that are essentially going to make our lives easier. So one area of particular interest at the moment are flexible electronics, as these allow integration of functionality into everyday objects. This is at the core of the Internet of Things construct, where you essentially have like objects communicating with each other. And you might see this in your own lives if you've got a smartphone connected to a wearable device or a smart home device. Thin film transistors, TFTs, form the basis of many of these electronics, and these are made up of layers of several different components. So you have your substrate, your dielectric, source drain, and a semiconducting thin film layer. This semiconducting thin film is made by depositing a semiconducting material and has previously been based on silicon and polysilicon glass technology. But to enable these advancements within flexible electronics, we want to be able to deposit the materials required within TFTs onto flexible substrates. So our current deposition methods, things like chemical vapor deposition, require high temperatures, and this means we are restricted to the substrates we can use. We tend to use things like glass that withstand high temperatures, but we want to be able to deposit these materials on flexible substrates like PET, as these have a melting point of around like 260, 300 degrees. So in order to do this, we need to explore different deposition methods and materials that are compatible with these deposition methods. So the process that we've chosen to look at is aerosol jet printing, and this is because it's a low temperature process, so you can deposit materials on a variety of substrates. And this works by depositing an ink that has a functional pigment. So pigments in traditional inks are things that give it color, but for us, our pigments are going to be precursors to our desired semiconducting materials, which are metal oxides. Aerosol jet printing works by first you aerosolize your functional ink. This then gets transported to the deposition head via an inert carrier gas, where it undergoes collimation and aerodynamic focusing before impaction onto the substrate. Once you have ink impaction onto the substrate, the solvent that keeps the ink fluid throughout the process evaporates, and you're left with a film of your precursor. This precursor then goes on to react with ambient moisture via this hydrolysis polycondensation reaction to give your desired metal oxide film. So as I've said, this is a low temperature process, so you have relaxed substrate restrictions, but it's also advantageous because it's cost effective, low waste, and you can create 3D devices. So currently in Bath, we don't have an aerosol jet printer, but there are some ways that we're going to do proof of concept work. So first, we're going to deposit materials using a Dematic inkjet printer, and we're also going to use this airbrushing coating technique. And the reason we can do this is because the formation of metal oxide is exactly the same as for aerosol jet printing. It is just the transport vector that differs slightly. For our materials, we're looking at metal oxides, and these are semiconducting materials that have high chemical stability and require low processing temperatures. So compared to things like silicon or organic semiconductors, so these are ideal candidates for printing materials. There are several key materials that we're looking at, things like titanium dioxide, copper oxide, zinc oxide, and tin oxide. But for this talk, I'm just going to talk about the work I've been doing on zinc oxide. So zinc oxide is an N-type semiconductor with a band gap of 3.4 electron volts. It is a transparent conducting oxide, so it's transparent at room temperature, and its stable form is a hexagonal work-site structure, which is shown here. It's a versatile material for electronics because you can form the P-type material through doping, and it exclusively forms the monooxide. So when you have tin, like you can form a monooxide or a dioxide, and that changes the electrical properties massively. But for zinc, we know we're always going to get the monooxide. It's also a good proof of concept because it's been used as a semiconducting channel layer in TFTs before, so we have something to compare our printed materials to. And as you can see from the graph here, which shows year against published articles, the interest in printable zinc oxide and zinc oxide for electronics has increased and recently peaked. In industry, when they're making zinc oxide, there are several classes of materials that are used as precursors. These are things like alkyl zincs, zinc halides, and zinc acetates. However, these will have disadvantages associated with them. So alkyl zincs are highly pyrophoric, zinc halides are corrosive, and zinc acetates are only activated at high temperatures. So these aren't going to be useful for our printed materials. So what we need to do is to develop precursors to zinc oxide films that are compatible with printing. And to do this, we need to fulfill a set of requirements for our precursors. So first and foremost, they need to form the desired material. They need to have low processing temperatures so we can print on our range of substrates. They need to readily react with water in a controlled manner because that's how we're forming our metal oxide. And it needs to be unreactive in the ink formulation and soluble in a range of volatile solvents. So aiming for this point here. The precursors that we designed were mono and bis substituted zinc-2 amino alkoxide complexes, and we looked at 5 different chelating amino alcohol ligands. These are inspired by common ink additives and solvents, but another reason we used them was because they have additional donor functionality at the nitrogen, so you can get coordinately saturated complexes, and this helps increase the control over reactions with ambient moisture, which is an important part of our process. So these are our 5 ligands that we looked at here. The first one, L1H, is a bidentate ligand, and the rest of them are tridentate. All of our tridentate ligands have the same core backbone. It is just the R groups on the central nitrogen and carbon adjacent to the OH groups that are changing, so we can look at the effective sterics from our complexes. And for all of these, it's the OH group that is the reactive site. To synthesize our complexes, we started off with this zinc starting material, which is called zinc HMDS. And HMDS just refers to this N-SiMe3 group here. And we can substitute our ligands for this HMDS group using an amine displacement reaction. So to form our heteroleptic systems, we reacted zinc HMDS in a 1-to-1 stoichiometry with each of our ligands. And this gave us complexes 1 to 5. We then repeated this reaction, but altering the stoichiometry 1 to 2 zinc to ligand to give our bis systems, which are complexes 6 to 10. We managed to get single crystal XRD data for all of our heteroleptic systems. These are our solid state structures. Complex 1 was shown to be a dimer in the solid state, whereas complexes 2, 3, and 4 were shown to be monomers. And this is what you'd expect. And this is a result of the increased chelating ability of the ligands that we're using. Complex 5, however, is also a dimer, which isn't necessarily what we'd expect because we're using a tridentate ligand, but this could be due to the fact that we don't have any alkyl substituents on our carbon adjacent to the oxygen. For our homoleptic systems, we managed to get single crystal XRD data for complex 6, which is shown to be a 2 zinc-centered system, 1 zinc with a coordination number of 4, 1 with a coordination number of 5. And then for our complexes 7 to 10, we used 1D and 2D NMR spectroscopy to confirm the identity. And we inferred they were this 4-coordinate zinc system, as we have a single ligand environment and no HMDS residual. We then moved on to do some thermal studies using thermogravimetric analysis, which essentially does what's in the tin. We heat it up, we heat up our complexes and see how the mass changes as we're heating them. So we did this for all of our heteroleptic complexes, which are 1 to 5, and we heated them up to 500 degrees C and just looked at how the mass changes as a function of temperature. So they all start off at 100%, and then you get to a point where they start to thermally decompose, and this is where you get your changing gradient, and this corresponds to loss of the ligand. And we hit this blue region here, and that's where we're thermally forming zinc oxide. As you can see, like all of our complexes are going below this blue area, which shows, and they give like low residual masses, which shows they are highly volatile, which is something we want in a printed precursor, because it means that the low temperatures we're looking to anneal at, we know that any unreactive precursor won't stay on the surface and give us like carbon contamination. And it's also a good indicator of what temperature these complexes are thermally stable up until, so we know they're not going to thermally decompose in our ink formulation. We then had to go making some films using this airbrush technique. So we used complex 2, which is shown here, and we made it up in 3 different concentrations. That was 0.05 molar, 0.1 molar, and 0.5 molar in THF. Deposited on glass using this airbrush, and then with like a different number of coatings, and we annealed them at different temperatures. So here are some images of the films that we've made, with the concentration of the ink down the side and then the annealing temperature underneath. And as you can see, as we're getting to like higher concentrations of precursor, the adhesion to the substrate surface from the film is like getting poorer. But all of these are currently undergoing PXRD to see if we've got crystalline zinc oxide on these films. So continuing on from this, we're going to continue with our material analysis. So get the results back from our PXRD, do some SEM work and some UV viz. We'll then use the Dematic inkjet printer to trial this precursor as well. And we're also going to do some DOSY NMR studies. And this will show us for our like complexes that were dimers in the solid state, whether they are dimers in solution state as well. So this is like a solution-based process. Our printing is, so the solution chemistry is important, and it might hinder the rate of reaction with water. So to conclude, we've developed precursors to zinc oxide films using ligands based on the ink species, based on species required in the ink formulation. We successfully synthesized and characterized a family of zinc 2 complexes, and we deposited one of our synthesized complexes using this airbrush coating technique. So I'd like to thank Dr. Andrew Johnson, members of the Johnson Group, the RSCGT and the funding bodies. I'd like to thank you for your time and be happy to answer any questions.